Hi, this is Mr. Royks here, and I'm going to take you through a practice problem that will help you be able to get through dealing with heat exchange during temperature change as well as phase change. So the problem we're going to be working on is asking us to calculate out the amount of heat necessary to convert 230 grams of ice starting at negative 10 degrees Celsius to water at 15 degrees Celsius. So first thing is think about the problem here. You need to think about your temperature. It won't necessarily always tell you that you're starting with a solid and going to a liquid. And if it doesn't tell you that piece of information, you need to think about that. So our starting temperature is going to be negative 10 degrees Celsius, right? Our final temperature is going to be 15 degrees Celsius. What you need to do is you need to think about where does that phase change come in? And the phase change, obviously, as you already know, is going to come in at 0 degrees Celsius. So when we're solving for these problems, you need to make sure that you're using the appropriate specific heat capacity as well as the appropriate temperature change. So in this particular case, I'd like to just kind of work this out. We're going to have a temperature change between negative 10 and 0 degrees Celsius. We're going to have a temperature change between 0 degrees Celsius and 15 degrees Celsius. And obviously, at 0 degrees Celsius, we're going to have a phase change. So what that means is I'm going to have 1 Q for the temperature change between negative 10 and 0 degrees Celsius. I'm going to have 1 Q for the phase change, and I'm going to have 1 Q for the temperature change between 0 degrees Celsius and 15 degrees Celsius. So I'll just go in that order. So starting with Q1, we're going to talk about the temperature change between negative 10 degrees Celsius and 0 degrees Celsius. Anytime you're dealing with a temperature change, the expression you're going to use is Q is equal to MC delta T, where M is your mass, C is your specific heat capacity, and delta T is going to be T final minus T initial. So if we look at the first Q expression, Q1, we have 230 grams times 2.05 joules per gram degree Celsius. That is going to be the heat capacity of ice and our temperature change. So remember that the final temperature as ice, as solid water, is going to be 0 degrees Celsius. So we'll have 0 degrees Celsius minus, and our starting temperature is negative 10 degrees Celsius. So 0 minus negative 10 degrees Celsius. And when we do the math on that, we're going to end up with an answer of 4,715 joules. So that's Q1. We're then going to look at Q2. Q2 is the phase change. So for the phase change, and again, you need to know which is which, but phase change between liquid and solid and liquid is going to be 334 joules per gram. And again, I will give you those values. You don't have to memorize that, which means that we, again, have no temperature change. So all we're dealing with is multiplying the mass, 230 grams, times your heat capacity, your heat of fusion, 334 joules per gram, and when we solve for that, we get an answer of 76,820 joules. Now we're looking at Q3. I wrote 2, but this is supposed to be Q3, and Q3 is going to be the temperature change. Now that we have it as liquid water, we phase change it to liquid water, and the temperature change between 0 degrees Celsius and 15 degrees Celsius. Again, it's another Q is equal to MC delta T expression. And so what we have going on there is we have 230 grams times the specific heat capacity of water, which is 4.18 joules per gram degree Celsius. And now our final temperature is 15 degrees Celsius. It starts off at water at 0 degrees Celsius. And so the value for that comes out to be 14,421 joules. All right, so now the last step is just tallying or summing these values to get the total amount of energy for this reaction. And the total amount of energy comes out to be 95,956. Again, In terms of sig figs, I'm going to base it off of this. I know there's no decimal point there. We'll pretend there's a decimal point at the end of 10 degrees Celsius. So we'll say that this has two significant figures. So I'm going to round my answer to two significant figures, and I'm going to call that 96,000 joules. Or again, we could write that as 96 kilojoules. So that's how you solve a problem that involves a temperature change as well as a phase change. See you in class.